Yogesh, sir.
Hello.
Sir, you can start with the webinar.
Very good morning to all of you. Today we will talk about there is slightly disturbance. I think some people are unmute.
Still, we are doing that process.
Okay.
Starting erection experience gain பண்ணாதான் உங்களுக்கு டிமாண்ட் பண்ண
So now we have done all the participants mute.
Okay. So let us start today for this webinar. Very good morning to all of you. I will talk about the construction of long span bridges. So generally, the bridges are built to meet the requirement, that is connecting 2 points and to hinder away from the hindrance. So functional needs of any site are specifically chosen, and then the spans are decided. Functionally acceptable minimum spans are normally chosen as those are economically viable. As we go on the larger span, the cost of construction as well as the bridge cost.
ஒரு 5 years 6 years இருந்தாலும் பார்ட் டைம் ஆனா PhD போட்டு விட்டுருங்க. PhD முடிக்கிறதுக்கு ரொம்ப ஈஸியா இருக்கு. அது முடிச்சிட்டீங்கன்னு வச்சுக்கோங்க.
Mereka akan menjelaskan semua sampai ke
Okay, can we proceed?
Yes, sir. We have unmute all the participants.
Yeah, but then sometimes they are anyway.
Actually, we have also done that process. No one will allow to mute themselves.
Okay. So functionally acceptable minimum spans are normally chosen, but sometimes also something like a point of attraction or something making a grand scale, that is also a reason to build the longer span. So nowadays the construction of these large spans is becoming popular, and it is also a challenging work for a civil engineer to build a longer span is definitely going to be a challenge. So bridging, generally see there are requirements of a large span. In case of rivers having very large flow, where constructing a foundation in between is difficult, there we chose longer span. In case of cities, we are finding that nowadays these railway yards are there, and we are building a bridge across a railway yard to cross that railway line. They are keeping span or smaller span with foundation in between of track is becoming difficult for the construction. So bridging large width of railway yard is without obstructing and hindrance of rail traffic, that is requiring a large span. There another requirement is also there. We can build a large span as well as we have to keep the depth of structure very less. Otherwise, the approaches on the either side of say railway yard will go longer. And generally in city, the space availability is very less. So we have to keep in mind that the superstructure depth has to be minimum and span has to be larger. Then in that case, the solutions available in conventional way is arch bridge, stratos cable stayed bridge, or cable stayed bridge. In case of cable stayed bridge, the depth of superstructure is very minimum, and ease of construction is another advantage in case of such railway line bridges. So construction of such bridges without hindering the rail traffic and taking care of the traction line above it can be done with cantilever construction by segmental bridges. Such solutions has been adopted in two locations recently. One is at Nagpur, that is cable stayed bridge at Nagpur railway station, and second very similar situation is at Bardhaman station yard, that is in West Bengal. Sometime, as I said earlier, aesthetic or something making a point of attraction, that kind of requirement is also there. So another third example I'll explain is the Durgam Shedbu cable stayed bridge. It is built across a bay in Hyderabad city. So overview of the presentation is like I'll explain these three case studies, and then the cantilever construction of steel truss, that is just taken for understanding of impact of construction method on the service design or whatever the member sizing and all. So that is very easy to explain as compared to the cable stayed bridges. So I have taken purposely that cantilever construction of steel trusses. So one by one we will go. First we will see the cable stayed bridge at Nagpur. So this is owner is MSRDC, Maharashtra State Road Development Corporation. It was built by Afcons Limited. PMC was right. The main cable stayed portion has one pylon and two side spans are, one is 88 meter and other is 112 meter. The standard carriageway is 11 meter and 1.5 meter footpath. The superstructure was cast in situ RCC superstructure with two longitudinal beams and the cross cutters and grillage type of arrangement. Segment by segment, cast in situ construction was adopted. Each segment length was about 6.3 meter, and cantilever form traveler what is, that is something peculiar or specially designed for that project. This is a photograph of bridge almost completed in phase 1. You will be able to see second bridge besides that existing old bridge that has many spans and all the piers are in between each track, and that was required to dismantle. So after building this bridge, that was dismantled and second phase also has been completed. For a large spans, almost that 88 meter span and 112 meter span, you will find that the depth of superstructure is as minimum as that the existing bridge is there, which has spans of say 10 or 12 meter or like that. So that is the advantage we can say in this cable stayed bridges. So this is the general arrangement of this bridge. There is, if you see the people from Nagpur may be knowing that southern end, there is an intersection coming very close to the proposed bridge. So the space, that longitudinal length available on southern side was very restricted, and hence the point of say P2, that height was automatically restricted because of the longitudinal slope, and vertical clearance is given by the railway for railway track, that cannot be changed. So available space for the superstructure is really very less. and there only this cable stayed bridge was only the possible solution. The pylon location was fixed considering the available space between the railway track, and hence the spans are not really symmetrical. The pylon was not perfectly placed at center, but that was not possible because of the railway lines. And then the you will find that one side span is 112 meter and other side is 88 meter. So almost imbalance of 24 meter is there. Number of cables because of this situation are different on either side. Then some part on 112 meter side is without cable also, so that much has been taken care. This is cross section of this cable stayed bridge. So there are two cable stayed bridges built side by side, each having 11 meter carriageway and footpath outside of 1.5 meter. This is at pylon section where the footpath is taken at the pylon location. In general, the cross section is like this. There are two beams about 1.8 meter deep, and depth of superstructure at mid of deck is just 1.2 meter. So we can imagine that for 112 meter span, the depth of superstructure available is 1.2 meter. There are the two longitudinal beams, and at each 6.3 meter there is a cross girder, and cables are put from these two main beams. The footpath is only on one side of each cable stay, so that is a unsymmetrical arrangement in transverse direction also, and there is unsymmetrical arrangement in longitudinal direction also because of the span unequalness. This is a longer view of almost completed phase 1 bridge. I'll explain in brief the erection sequence, whatever it has been used there. So first pylon is completed. Then to start the deck erection, first some up to first cable, that is around 12 meter, staging is erected like regular bridges. This is the staging is erected. On the top of staging, some beam arrangements are made. On top of beam, conventional shuttering is placed. Then anchorage is placed, reinforcement is placed, then concreting is done. After doing the concreting, after concrete achieves the strain, some hanging arrangement is made. These two are the hangers which are connected to the lower beams, and they are supported on the completed concrete work, that is longitudinal beams. Now some additional shuttering part is also connected further. Then on the top of completed deck, one truss type erection crane is erected, that is on the top of deck. There is a connection made between the bottom beam and the top truss. Then the first cable is traced. Now after first cable is traced, the deck is supported on a cable, and that is not requiring any support from below. So, and the shuttering beam or staging beam, whatever are there, they are hanged up to the beam with two hangers and one more front hanger which is supporting on the truss on the top of deck. Now it can be lower, so some gap is created between the beam, and that is possible to move further. So now the shuttering is at next place, and it is not requiring any support from the ground, so it is free from any support below. Now that movement has been also done. Now the next segment of concreting can be done. So some arrangement was this exchange of support, etc., was required. This is then the total staging below is cleared off, and the obstructed railway track has been now cleared. It is operating below this staging. Now further this has been moved to the next place, then raised to the beam level. So now shuttering is ready for next concreting. But there was an issue that the reaction transferred by this staging system or that staging beam, shuttering beam to the deck was very high. So one cable was required to be introduced as a temporary cable to support the beam at front level. So whatever load of concrete will come here will be shared by this point as a cable that will be transferred directly to pylon, and some part will be shared to the actual concrete behind that. So this is a tie rod which connects the and positively to the existing deck that already constructed deck. So some reaction is transferred here and some reaction is transferred to the cable at front point. Now this is ready for the concreting of this 6.3 meter. Now again for next segment the anchorage is placed, reinforcements are tied, and conventionally concreting is done for these cables that segment. Once the concreting is done, the stress in the cable goes on increasing and this point also goes on down. So now again the same procedure will be repeated till the end of bridge, and this is symmetrical for the presentation purpose, though it is shown on one side. This has been done symmetrically. So there are two such sets, and one is on 88 meter side, one is on 112 meter side. So there is no hindrance to the rail traffic. Only during the movement of this cantilever formwork, there was a requirement of a railway block. Otherwise, the construction goes without hindering the rail traffic. That is the main requirement of any railway line. Nagpur, you will be knowing that this is a main station having used railway traffic, and Rajdhani route is also there. So blocking for a long time was not possible. Then the second cable is introduced. Now the important aspect of any of such construction is ultimately we have to achieve the required shape, whatever I have shown in first GAD slide. That is the aim. We have to achieve the shape of a deck in the form of a smooth curve or having a riding quality smoother. Then we have to plan the geometry while constructing as per that aim. So we are aiming at a curve say 0, 0, and this is shown in dotted line. Then for explaining this geometry control, let us understand through a simple cantilever theory. Suppose there is a fixed end cantilever at this segment S1, S2, S3 we have to erect. Then once we erect a segment S1, the tip of S1 will go slightly down. So this is the first point down. Now when we erect S2, because of the weight, this will go further down and the tip will go, tip of S2 will go something there. Similarly, when S3 is installed, the further it will go, and this is being continued. Now the similar is other way around also. We will stress the cable from S1, it will go up. S2 will stress the cable, it will go slightly up. So theoretically we can decide to achieve the aim of say 0, 0, how much we have to make pre-camber. So pre-camber is a shown light in this curve. So whatever net deflection due to self-weight of segments plus upward deflection due to cable stressing, that net whatever we'll get will exactly place the reverse as a camber curve, and we'll plan the casting of day in that reverse manner. So that is called a camber curve. In general, we can say that the camber, there, if suppose there is a continuous span, there will be deflection due to all permanent load, that is self-weight, pre-stress, stay cable. I am talking of now the first we see the construction camber. Now we are looking at the camber of permanent load also. So there will be some permanent load deflections is also there. Now we have to reverse that also. So ultimately we have to add this camber also while constructing construction stage, and we have to achieve the pre-camber stage like this at the end of construction. So this is a exaggerated shape. So we will achieve at the end of construction such shape which after say permanent load, wearing code, then whatever superimposed dead load like crash barrier etc., those will come and it will come almost flat. Then there is a deflection due to creep of concrete also, which is also considered, and accordingly these Camber diagrams are decided for service stage and the construction stage. Now once we are ready with the Camber diagram of bridge during construction, we have to achieve it in site to ensure that at the end of construction we are at whatever aim has been put, that we have achieved. So theoretically whatever we have planned, that has to be given in the form of drawing to site. So theoretically expected beam top levels at each 2.1 meter are provided. That each segment was of length 6.3, so 1/3 at each point, that is 2.1, that was provided. Then those are monitored during construction also. Apart from that, there is a deck deflection due to temperature also. So you will notice that without any activity, the deck in the morning is having some different level, and in the afternoon it is having some different level. So there is a deflection due to temperature variation during daytime, and that deflection has to be also accounted. Then theoretical readings are whatever the levels are given are cross verified at site, and whatever the difference are there, that are reported to the designer, and then the corrective action can be decided. So the correction can be in the form of, say, additional force in previously installed cable, or planning some extra camber in next segment, or mixture of the both that can be done. So based on the stress level and all, that decisions are made. Similar to the deflection of beam, pylon deflections are also required to be monitored. So pylon readings are taken at regular interval and at fixed height location. So this is a view of completed bridges. The 2 bridges are completed. Second bridge, I think it was opened later, and then that was the photograph at that time. There is one video, I'll show it at the end of this presentation, that bird's eye view is shown for the entire this cable stayed bridge. Now we'll move to the second bridge, and this is similar to whatever Nagpur has been done. So this is at Bardhaman station on Eastern Railway. It is in West Bengal. The situation at this is very similar. First I'll show the slide this. So if you see that there is a railway line, almost 14 or 15 railway tracks are there, and the pylon is built outside the railway tracks. The authority who planned this had visited Nagpur during construction of first stage of this cable stayed bridge, and then they decided to take out the pylon construction outside the railway line, because pylon construction takes longer time, and then there is always risk to work near the railway line. So the span arrangement here was adopted, was more eccentric than the Nagpur. In Nagpur it is 112 and 88 meter. Here is, because of the site constraint, it has become 124 as against the 64. The other side is 64. Then there is a requirement of 2 carriageways, 7.5 meter wide, and those are built in a common cable stay. Like Nagpur, there are 2 separate cable stay. Here, this is common. So if you see the general section arrangement, there are 3 pylons and 2 carriageway, 7.5 meter each. The third pylon requirement was introduced because of the very shallow available depth. The beam depth available is just 1000 mm at mid, and that could not be done without the third pylon with, say, 15 meter carriageway and all. So the third pylon was introduced, and the depth, they have taken one more decision, that backside of this, so this is a concrete part, this is a concrete part, this is a concrete part, having a very heavy section, and from here onward it is a steel composite construction. So there are two advantages: that unbalanced force is minimum because of the lighter weight of steel sections, and the backside is having heavier concrete section, so it is balancing weight to the some extent. And the pylon above the deck level is totally in steel, so this portion is steel totally, and this is a steel composite deck, and then the integral span is provided beside that. So this is outside totally the railway line, so construction can be done without any hindrance with the conventional staging and shuttering form. So the cross sections of deck look like this, that on front side the steel rectangular boxes are made. This is a one beam, this is another beam, this is another beam. On the top of it, deck is constructed. So this is a deck is constructed, and these are the cross girders provided at regular interval, which are made monolithic with using shear connector to the concrete. The mid beam is connected to this deck with side shear connector. There is no top of on the concrete. So analysis of this type of section is particularly very tedious. The original design was done by CES, and Stup was involved in it as geometry control during the construction. So the main role was to achieve the perfect geometry at the end of construction. Cross section of back span is there are three heavy beams, almost 2 meter, 1.8 meter deep. Those are the solid concrete section, and deck slab is also heavier. That 750 thick RCC deck slab is there. The purpose is to balance the weight of say 124 meter on front side versus 64 meter of back span. So that was the purpose on making such heavy section. So we'll go back to introduction. So this was the cross section generally. Then the deck slab on the front side was made of. Yes.
So sorry to interrupt you in between, but
Yes.
in chat box we are continuously receiving message regarding the voice. So it is possible for you to use a headphone?
Yeah, I am using headphone only.
Okay, then fine.
Any else setting is there to increase the sound?
No, sir, nothing else than that. Just to confirm that I have interrupted. Thank you.
Okay. I'll come. I'll try. Anything is there? I don't think any setting is there.
No, there is no such setting, sir, in between.
I see. Okay. So now the I'll talk little louder then.
That will be more better.
Yeah.
Sir.
So width of decks is almost 28 meter wide, and 3 pylons are there. So 3 planes of cables are there. Then the main side of the span is precast. RCC planks are placed. So there is no cast in situ construction apart from the top layer of this deck slab. So that was the beauty. They had taken all these decisions after looking at this Nagpur case study, and some configuration was changed at later date. So that was the advantage that we have seen. This we have seen. So there are 2 common piers and one between the pylon. CP1 is say backside, that is integral. Only CP2 side there is a bearing provided. Otherwise the deck is monolithic with substructure. So there are 3 steel pylon as said earlier. Now the erection of completion of this backspan is very easy as compared to anything, because that is outside the railway boundary and there is no hindrance of railway traffic. So that was done with without anything. The front span erection was done with a specially designed deck erection crane. Like in Nagpur, that shuttering arrangement was specially designed. In this particular year, the steel girders are used. So erection of steel girder on railway track above the traction line was done using a deck erection crane. I show the pictures of deck erection crane so that it will be understood very easily. And one video is there which will explain this construction sequence in a easy manner, and it will be easy to understand for everybody. So these are some drawing snapshots from the construction stages. Instead of showing this, I'll just go to that video and then we'll come back. So this is a specially designed deck erection crane which is used for erecting those segments. Are you able to see the video?
Yes, sir.
So the backspan is ready. Now this is used with the conventional, and that concreting etc. is ready. Now we have to erect this each segment by the specially designed deck erection crane. So these are the pre-fabricated steel members, what are that rectangular boxes we have seen in earlier slide. Those three are first erected, then those are bolted, and those are temporarily held from some temporary arrangement. These are first cross girders are placed, and then the precast planks are erected on the top of it. Before that, the permanent cable is stressed. So now we have seen that how the deck erection crane works, and over the railway track, nothing is freed from below, only backfeeding is done. So whatever completed span is there, from that side only that feeding is done. And then the regular interval, this erection and cable stressing, etc., goes on till the end of that's a span 124. Almost 10 segments are there, and that was erected in a time schedule of less than 1 year or so. So this bridge has been completed very faster as compared to this Nagpur because of the construction methodology. They have changed from concrete to steel composite construction, and the pylon also they have made it in steel, and the whole pylon has been taken outside the railway boundary. So there was hardly any entrance to railway traffic, and safety was also ensured during the initial stage itself. So that's how the erection of this bridge was completed. This is a view of side view of deck erection crane. That was weighing about 180 metric ton, including 30-35 ton of back weight. That is a counterweight for stability of this crane. So that was put on the deck. These are photographs we have seen, then video we have seen. So in analysis, all these whatever planned construction sequence has to be captured. So backspan is constructed, and those are placed on the staging itself. So staging has to be modeled, then staging beam, etc. Those were need to be modeled. Then the pylon, cables, etc. as a regular thing in model. Then the segment by segment direction is also modeled in any software. Nowadays, commercial available softwares like Lusas, Midas has this capability of modeling stage by stage construction, and using that all the stages are minutely modeled and studied the behavior of structure during the construction. Whatever the loads are coming there, that has to be precisely estimated during initial stage itself, because any addition in the load will be multiplied by, say, that cantilever length. Suppose if we have estimated a deck erection crane of 180 ton, and it becomes, because of say some fabrication issue or something, 200 tons, and 20 ton is increased, then 20 into 124, that much is the moment increase overall system of this pylon. So the load estimation has to be very precise, and all the load cases that stage by stage construction, whatever sequence is there, that has to be monitored. So this is a view from analysis model. This is rendered view of the model. In steel, there is no change in properties during any time, but concrete exhibits change in its property. It goes on increasing the strength. So 3 days strength is lesser than 7 days, then 28 days. That's what it goes on achieving the strength. Then there is another factor that is more governing the deflection is the creep of a concrete and shrinkage of a concrete. So those has to be considered. There are many formulations in the internationally available. Nowadays, mainly the CB-FIB model is being used, and now it is introduced in IRC codes also. So these creep shrinkage are actually considered in the model, analysis model. So the deflection should match closely to the theoretically whatever we have estimated. Then again, like Nagpur case, here also this geometry control was required to be monitored at every stage. So it was a target to achieve the design profile without any overstress of the various structural elements. So that was the aim of assignment. So that can be achieved by pre-camber, but here the decision was taken that pre-camber in steel girders was difficult. Otherwise, that side, that bolt matching, etc., may mismatch, and so the decision was taken that pre-camber will be done using cable forces only, and accordingly, the cable forces were analyzed, and those were applied in the cables. So the theoretical profile of the deck is verified at each stage. So typical cycle of erection is like erection of first is a panel, then stressing of cable, then concreting of each panel, Then the backspan was traced, next segment cable, and then the crane was moved to the next segment. That is a typical cycle. So at after completion of each activity, the levels were recorded along with the temperatures. Whatever site temperatures are there, those were recorded. And then the comparison is made with whatever estimated deflections are there from theoretically. Then the corrective measures in this case could be taken by two ways only. That correction, if pylon has say deflected more on that 124 meter side, then it can be effectively stressed by the backspan cable. So we can stress something more in the backspan cable. Accordingly, some extra margin was left in the cable. Some additional strands were made arrangement for those are called dummy strands. If required, those will be used. If not required, those will not be used. Like that was planned. And the geometry of front panel, that could be done only through the adjustment of front cable forces. Here, because of the quality control of steel material that is manufactured in a very good manner, so the front panels were behaving more or less whatever estimated is there. So there was no requirement as such to adjust much in cable forces, and it went well. Not even noticeable, but that was adjusted in bearing code to give a smooth riding quality, and that's how the geometry control was achieved there. This is a picture of 3 pylons during construction. This is a completely steel pylon, and the cables are anchored inside a hollow pylon. So pylon is hollow, and cables are anchored inside the pylon. Then there are cross members at 2 levels. One is this, one is at this level. Stressing is done from inside. So inside the top, I don't have the exact pictures. Otherwise, that was a very cumbersome arrangement because the space available was very less, and the stressing was done inside of the pylon. So that arrangement was slightly cumbersome. Otherwise, every other details of this page are really very useful for any planning further. This is another side view of a bridge during construction. Deck erection crane during the operation over platform. You will find that the trains are moving below and erection activity etc. is going on very smooth because there is nothing to be fed from below and there is no any disturbance to rail traffic. Only during the movement of this crane to the next position, some power block as well as rail traffic block was taken. Now, after completing these 2 similar bridges, we will go to third example, that is extra dose bridge over Durgam Chedu, Hyderabad. Then we will understand also the difference between extra dose and cable stayed bridge. Both are basically cable stayed, but then there is some difference between the two. This bridge is built not only for any functional need as such. I mean, we had seen in first slide that bridges are built for the functional need, etc. But then this was built something as a truly architectural requirement. So this has been built with the main focus on its aesthetics and of making some grand. So this there is a lake, and keeping construction feasibility, the pylons were planned, and the span is about 234 meter long. So the distance between the 2 pylons is 234 meter, and then the backspan, depending upon the availability, these were chosen. Those are not exactly balanced. For say 240 meter span, backspan should have been almost 150 meter or so in general practice, but because of the land constraint, that span is again unbalanced here. So all the 3 examples, whatever we have seen, those are unbalanced type of bridges. But that can be built. So that has been done accordingly. So the span arrangement is 96, 230, 3 and 96 meter. Total is 425 meter span is there. The deck has been given shape of a fish belly. You will find that the smooth profile has been provided all along its seas. These are ribs provided at intermittent. Next picture that will be more clear. So the deck is 25 meter wide, that is on a single box and single plane of cable. So that is the challenging work, that handling of such heavy segments and erecting it, that was also a challenging work. So total width is almost 26 meter and span is 233 meter. Then the pylon has been given with some aesthetic view, that lighting arrangement etc. on the top of it, and the cables are given in fan shape like this. Now here I'll say the difference between this earlier cable stayed bridge and this extra dose bridge. If you notice, say in Nagpur, one span is 112 meter. So hypothetically, if we plan, say there is another pylon, hypothetical case, so span will be double, say 112 become 224. So central span will become 224. Here the central span is 238 meter. So that is comparable. Pylon height in Nagpur case is almost 45 meter. So say span of 240 by 5, almost 45. So span by 5 is the height of pylon there. Whereas in this case, the pylon height is very less. It is half of that Nagpur case. Here only 25 meter is the topmost cable is placed from the deck. So it is half the height of the deck. So this is called extra dose bridge. If you see the elevation, the angle of cable with respect to horizontal deck is very flat. Whereas in Nagpur or that Bardhaman elevation, you would have noticed that the angle is more steeper with respect to the horizontal. So the angle of cable with respect to the deck is a differentiation between these two. That is the, for understanding, the difference between the two cases, that is extra dose and cable stayed bridge, is mainly because of the force transfer mechanism. In case of steeper cable, that is almost vertical cable, more force is transferred through cable itself and lesser through the deck. Whereas in this case, the deck is also steeper. If you notice, the depth of superstructure, that is cross-sectional depth of superstructure, here is 4.5 in the mid, and at the root it is 8 meter. So for the comparable span, say Nagpur is total depth of superstructure there was almost 1.8 meter, whereas here is 4.5 to 8 meter. So deck is steeper, and deck is also carrying more load as compared to the cables. So fluctuation in the whatever the forces in the cable are lesser as compared to the cable stayed bridge. So the consumption of these external cables, which are very costly because of they are imported, that becomes cheaper. So this kind of structure becomes more cheaper, but then you will find that the depth of superstructure is more, which is not feasible in case of railway line crossing or so. Otherwise, it requires longer approach times. So considering the economy and the constraint, we can either plan extra dose bridge or cable stayed bridge. This is some animated view what has been planned earlier. So you will find that there are ribs at regular interval, and the pylon is integral. There is no bearing provided in between. So pylon is integral. On the top of it, some lighting arrangement. Then on deck also some lighting arrangement is shown. Also there all these railing etc. Those were derived from aesthetic point of view. So everything of this bridge was mainly derived from aesthetic point of view rather than that requirement of functionality. This is the view during construction. The main challenge in the construction was like the two pylons are planned on edge of lake. So backside spans, they could have been erected like regular on staging support. Erection of these segments inside the lake was a challenge. So what they have done, L&T has constructed this bridge. They have made a casting yard nearby here only. They have this floating barge, shallow depth barge is there. So that carries the segment, and there are two deck erection cranes. The simultaneously erection is going on from the two sides. The back span is first erected on the staging. They are internally cables are stretched, and the external cables are one by one installed on either side. So the segment by segment erection is done. This is a closer view of segments during the erection. So there is a specially designed crane here again that is lifting a segment up to here. Then this is second frame for people to stand, and there will be some cables and all erection will go on. So for that work, people has to go there. So this kind of crane has been done. You will see the barge also there, which carries the segments from this casting yard nearby to the place of erection. So that can be seen here. This is top view of that segment erection. So up to now we have seen the three case studies. One is Nagpur cable state bridge, then second is Bardhaman cable state bridge. Both were almost similar except the material chosen for the construction. That is, first one was totally RCC deck, whereas second one was steel composite girder. The third one is extra dose cable state bridge, and that is pre-stress segmental also. So those are all segments done, and internal pre-stress is also there. With the internal pre-stress and external cables, this kind of extra dose bridge is done. We have seen also the difference between the type of these two bridges, that is cable state and extra dose. That is height difference in the pylon as well as superstructure cross section depth. In case of extra dose bridge, the superstructure is more, you will say, having more depth, and in case of cable state bridge, the depth of superstructure is lesser, but height of pylon is more. So based on the requirement of site, anything can be chosen. Based on economical constraint, the extra dose bridges are more economical from material point of view. So now, to understand the assessment of all these construction method, I have taken example of cantilever construction of steel truss, which is very easy to understand what does mean by the stage by stage construction analysis and what is its impact in the design of any bridge. So to understand this, we have taken this example. Say this is a Patna bridge for railway. You will understand that the first span on land side, this is the land side, and then there is a Ganges. So land side span is completed using conventional staging. This span is completed. Okay. Then the erection of second span is going on. So in erection, you will find that the truss is connected with some linkage. The linkage is provided at top, and then the material is again fed from backside or by floating barges there. So anything can be done. In this case, I think floating barge has been used, and this material is given. So then each node by node, they will go on erecting till the end of this span, that is reaching to the next pier location. After reaching to the next pier location, this link will be removed. The span will become simply supported. So during construction, it is a cantilever, and after completion of the erection of this cantilever, after removing this link, it will become a simply supported one. Similar case is another bridge, that is MG Setu, recently being built. Construction is going on. Afcons is constructing this bridge. There, one truss is completed in between, and there are two cantilever linkages provided, and on either side, the cantilever construction can go on. This increases the speed of construction on both ends. So this is typically, in earlier slide, if you see, we have to build one span and go on constructing on one side only. Whereas in this case, some mid span is constructed first, and then on either side of it, the span can be go on constructing by cantilever erection. So the difference between the two, this is after completion of one side each span. In analysis, this is very simple to understand. So in first case, say I have done exercise for 122 meter span. So first 122 is simply supported, erected, completed span is there. Now this erection is going on for this second 122 meter span. So that is a cantilever at 122. Then the bending moment diagram will go like this. Then there will be some overturning at this point of view. To avoid that overturning, we have to put some cartilage here. That is obvious. So bending moment of this looks like this. In second case, the same 122 meter span, if we cantilevered on both sides, the bending moment will look like that. This is easy to understand. Then there is no requirement of cartilage because that is balanced on either side. Okay. But if you see the bending moment at this mid span, this was having this ordinate, that has increased this much. Almost the flat diagram has gone. So the weight of truss, that is requirement of member, is higher in this case. So the quantity of say truss is say 1242 metric ton in this case. It becomes 1450 metric ton in the second case. That can be avoided by some other option. So the same truss is analyzed for next stage. That is, some weight has been proved. So this is the diagram for cantilever, two cantilever and central span. Then some additional cartilage type load is given here. So the bending moment diagram will come like down. Then again we'll find that the quantity is 1242 metric ton. But mobilizing that much of weight on this span may not be feasible. Then what is to be done? Then some option was done like one span full is done, one span is half like done, and some part cartilage is given. So that kind of study is also done. So in both the cases with some cartilage, the quantity or the requirement of strengthening, additional strengthening for the construction is removed. Now in case of this cantilever construction, after removing this, suppose this truss reaches here and the support is activated and the link is removed, then both the spans will behave like a simply supported. So bending moment diagram then will be the hogging one, sagging one instead of this hogging bending moment. So redistribution will take on. But in case of cable stayed bridges, this redistribution doesn't take place. So whatever deformations and whatever will come, those will be locked in stresses. So in case of cable stayed bridges, analysis has to be done. In case of say these trusses, the service analysis can be done separately and construction stage analysis can be done separately because the behavior of the two stages are entirely different and they are not connected on each other because the stress is redistributed after removal of the linkage. But in case of cable stayed bridges, that whatever construction stage at the end of construction stage, whatever the stresses are developed, those are locked in stresses. So that has to be assessed properly. And the assessment of, or rather the service design will carry forward those stresses. So the service design cannot be done ignoring the construction methodology and construction stages what you are adopted. So in any bridges, this is just output of whatever we have seen here, that one span, two span modeling, then uniform load is applied. Then whatever the bending moment diagram, that difference you will see, like what I said, when the two spans are there, whatever the bending moment alternative here is just 1/3 at other case. So strengthening of this that analysis is shown here. So now we are at the almost concluding session. That construction sequence has great impact on the design of structure, and construction of long span bridges needs very meticulous planning on the construction aspect and its effect in the design. So design and construction planning has to go together. It cannot be separated. The behavior of superstructure during construction as well as during service are different, but then analysis need to be carried out considering the detailed construction activities and whatever locked in stresses are there, they should be carried forward for the service design. In case of say this cantilever construction of steel trusses, there is no requirement of considering anything of those stresses in service, because the service after removal of linkage, it will become simply supported again. So redistribution will happen. But in case of cable steel bridges, that cannot be done. Then the important aspect, another important aspect is concrete property. So with respect to the age, concrete exhibits different property. It goes on achieving some strength. Also, it develops elasticity more during say initial stages. After say 28 days, more or less the strength will remain constant, E value also, but there is a creep factor which changes the deformation of structure. So it redistributes the entire scenario. So that has to be properly modeled. Then important aspect is theoretical, whatever has been aim is put or whatever has been achieved, that has to be continuously monitored at site. And if whatever the assumptions in the analysis, those are not matching with site results, those has to be corrected. Like in initial stages of any bridge construction, we find that there is considerable difference. Then we check with respect to the actual concrete strength and value of elasticity of concrete achieved vis-a-vis whatever we have considered in the analysis. That is the first check. Then second check is about density of concrete. Then the third check is what are the forces applied on the cable, that is pre-stressing force applied on the cable. If those are the similar way, whatever we have assumed in the analysis, and those, that can be monitored. And once it is tuned, it is find out that in this 2 or 3 projects, it is find out that more or less the theoretically whatever assumptions are there, more or less those are matched at site. And still some differences come. So some during analysis itself, some extreme value consideration has to be done. Like it is called sensitivity analysis. Sometimes you will find that deflections are more than whatever predicted, sometimes lesser. So some engineering judgment has to be put. What is the effect on overall structural stability because of some extreme cases? So that is called sensitivity analysis. And if that is done, then probably there should not be any issue as such. But then continuous monitoring vis-a-vis comparison with the theoretical has to be done. Then necessary correction in the profile has to be done stage by stage. We cannot leave that we'll correct only at the end or something like that. So each stage we have to make the correction and go further if the difference in theoretical value versus actual value is more. Considering that, this is what I wish to say. And thank you to all of you. I'll show one of the video for this Nagpur cable stayed bridge after its completion. And then we'll go for question answer session if anybody want to ask any question. Are you able to see the video?
Yes, sir.
So this is a Nagpur station area. Drone shooting has been done after completion of second phase of bridge. There are, I think, 7 or 8 platforms, and more than 15-16 lines are also there. Okay, then any questions there? I can
Yes,
take.
sir. It was a very nice